Okay, hello everyone. Today I will be streaming Leetcode Weekly Contest 238. This is like my first sort of screencast, so we'll just see how it goes. Um, I'll probably explain the problems a bit while I'm solving them, and then afterwards I'll explain them more in detail once I solve all 4 problems. These problems usually aren't that hard, so it shouldn't take me very long to do them. But sometimes the number 4s are kind of annoying, so we'll see. Alright, starting in 5 seconds. Cool. Okay, sum of digits after converting from n from base 10 to base 8. Okay, we can probably just do a while loop for this. Create an answer. And mod k. I think this should work. Okay, cool. Number 2. Frequency increment. Return the maximum possible frequency of an element after performing at most k operations. Okay, so our length is at most 10 to the 5th. Interesting. I think we should probably try to convert everything we can to the median. Or the mean. Let's see. Hmm. Okay, so I guess for each number, we can try to make as many elements as we can equal to that number, and then we can return the maximum. And I guess I'll have to update this in like 001 or something. Okay, so our bounds are 10 to the 5th. Create an answer. I'll create a cur variable if there's a maximum we can make equal to I after k operations. So we essentially have to store numbers less than I and numbers greater than I, and then essentially convert k of them to I think. And oh, you can only increment the element, huh? Oh, okay. Use an index of nums and increment the element at that index by 1. Okay, wait, so then we have to make the answer one of the elements of nums, I think. It would be suboptimal to make it not one of the elements. Okay, so I can just run a loop for this. I can sort and then run a loop. Okay, I have to sort and then I have to binary search. So I equals I. And essentially, I should create a prefix sums too. Vector nums.size. Make this long. Okay, so over here, basically we have like, let's say we have like nums0, nums1, etc., right? And we want to make them equal to nums k. Obviously, elements greater than nums k, we can't make it equal. So we have to make some sort of like contiguous a segment from nums k down to like nums x equal to that, because we want to make numbers close to it equal to it first because that takes less operations. Okay, so int mid is equal to low plus high over 2, and we can check if make mid to I equal to I, right? Equal to nums I. So the number of operations that would take is nums I times the length of this range, which is I minus mid plus 1, right? Minus the sum from mid to I. So minus the sum along remove is equal to nums, or prefix of mid, which is basically prefix of I, minus prefix of mid minus 1. So if it's equal to 0, then we don't subtract, so rem minus equal to prefix of mid minus 1. And so if this is less than or equal to k, then what can we do? Then we can extend mid to the right, I think. Or sorry, we can extend it to the left. So high is equal to mid. Otherwise, if it's greater than k, then mid doesn't work, so we have to make it equal to mid plus 1. See? Okay. This should work. And essentially, we set answer max answer I minus mid plus 1. Then return answer. Okay. Yeah, hopefully this works. Shoot. Oh, I'm putting this too low. Three, two, one. Okay. Submit. Oh, cool, accepted. Okay, number 3. String is considered beautiful if it satisfies the following conditions. Each of the 5 vowels must appear at least once in it. You must be in alphabetical order. Okay. So each appear at least once. They're in alphabetical order, so it's sorted. Length of the longest beautiful substring of word. No substring exists. Return 0. Okay. Cool. Okay. So we can probably just do this in O of n. I'll create a last so I should probably assign this to infinity at first, right? Or basically greater than word dot size. So we want to calculate the maximum j such that if I is the right endpoint of our substring, then the range j to I satisfies our condition. So essentially, j has to be greater than or equal to the maximum of elements in last. And last basically stores the last occurrence of A, E, I, O, and U. So I'll update that first. Last 0 equals I, E. This is not a very efficient way to do it, but whatever. Oh, last 3 equals I, else last 4 equals I. Okay, and now let's calculate int j. Set that to I for now. And we also need this range to be sorted, right? So I'll create this last sort variable is equal to 0. Oh shoot, I don't think this works. Okay, Um, hmm. Oh, I suppose we could we use 2 pointers? So we start a pointer here. So if we try to use 2 pointers and we start a pointer here, we go AEI. This doesn't satisfy, so we have to break out of it. Then this doesn't satisfy, then we go here, AAI. We have to reach E first, right? So that won't work. So then we break out, and then we go here, 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 AEIOUU. Okay, I think 2 pointers works. So I'll do this. 0 r equals 0 while dot length or dot length okay, so basically we extend R until it doesn't satisfy our range L to R. So while R is less than word dot length, and let's store the number of, let's store the last basically of this that we have. So like A maps to 0, E maps to 1, and so on. So I'll store this start last at -1. Stop this. Okay. So if let's see, if word of R is equal to A, I'll just create a I'll just transfer this into a vector of nums, or like I'll just map this to 0, 1, 2, 3, 4 right now, instead of doing that later. Equals 0. Nums I is equal to 4. So if nums of R is equal to last, then we can extend R, right? Else if nums of R is equal to last plus 1, we can also extend this. Otherwise, we have to break. Okay. And then I'll subtract 1 from R here. And let's see. Okay, so now our answer is going to be the length of this range from L to R. So max and R minus L plus 1, right? And now we have to add 1 to L. We have to update this range. So basically what we did here is we basically, oh, we also have to make this last 5, right? Last plus plus. Okay, so if last is equal to 4, sorry, then we do this because we hit, it basically means we hit, we have something like A, E, I, O, U. So we're at a 4 over here, and then this next element will be like an E or something, meaning we break out of it, and we have this range. And now we add 1 to L, so we'll have this, and, or basically we have this range, then we can just set L to R after that. So L equals R plus 1. And we should just return an answer after that. Judging. Oh, okay. I probably have. Let me print L and R. Oh, maybe I should change this to length. Oh, 3232, okay. Oh, I should also set R equal to L. 33. This is probably on the first case, right? Oh, and we should set last equal to -1 too now. Okay, let me try this now. Oh, I see what it's doing here. Okay. So I'll have to create a separate condition if the last is not 4. I'll do this here. Otherwise, let's just set L. L is equal to R plus 2. So otherwise we have something like A, E, I, and then E. So the R goes over here, so this range works. So if R is greater than or equal to L, then I'll do this. L is equal to R plus 1, and R is equal to L, last equal to -1. Otherwise, then we basically broke out at the very first instance. So we broke out over here. And I should just move L forward 1. Okay, let's try this. Okay, now we stop at 0, what? Oh. L is equal to R plus 1. Okay, 1350. Cool, 1350. Let me move this. Okay, let me submit. Okay, cool, accepted. Okay, number 4. You want to build n new buildings in a city. The new buildings will be built in a line labeled 1 to n. However, there are city restrictions on the height of the new buildings. It must be a non-negative integer. The height of the first building must be 0. Height difference cannot exceed 1. Okay, initially there's city restrictions on the maximum height of specified buildings. These restrictions are given as a 2D integer array, where restrictions I is equal to IDI. Oh, there was a code for this problem similar to this. Okay, so we return the maximum possible height of the tallest building. Okay, so I guess, let's see. So I suppose what we could try is some sort of maybe binary search on the tallest. See if there's constraints on this. Okay, 0 to 10 to the 9. Okay, So we'll put the first building as 0, and then the second building, if its max height is 0, then we have to keep it at 0. Otherwise, we put it at 1. Now the third building, we can either plus 1, keep it the same, or subtract 1. Okay, I feel like we can sort of do a greedy strategy where we'll add 1 to the previous building height, and if that now exceeds its max height over here, then we'll just set it to the max height, and then we don't really care about the previous ones. Okay, so I'll create a restriction. We'll do a max here, and I'll just get the elements from here and put it there, so I can just store by index. Restrictions.size. Restrictions of I of 0. Minus 1 is equal to restrictions of I of 1, right? Okay. So now, current is equal to 0. So now from 1 to n, basically set the height of building I is equal to the minimum of restrictions of, or max of I. I'll fill this with 10 to the 9. Okay. So we set it to the minimum of the restriction that we have on building I, or building of I plus 1, height of I minus 1 plus 1. And we can just return height of n minus 1. Let's see if this works. Seems like a really cheap solution. 2, 5, 3, 2, 5. Oh, okay, this is 5. Oh, the tallest building. Oh, shoot. Okay. Okay. This isn't the tallest possible height for building N. I misread. Also, N is 10 to the 9. My bad. Okay, so you have to think of a fast solution to this. Okay, so what I guess what we can do is we can sort restrictions by increasing ID. And so this restriction is obviously 0 for building 1, and now let's look at like the next building with the restriction. Let's say it's building X. Then we want to sort of go in a pyramid fashion, where we go from 0 to like some number, some peak, then we'll go down, and we'll try to meet the restriction. And then after that, we do the same thing from building X to the next restriction, and so on. So let me try that. Oh, okay, this is gonna, I should sort by the ID, right? Yeah, okay, so this is gonna sort restrictions. That's fine. And, cur is equal to 0. So this is the last, basically. And now, I'll set an answer to 0. So we basically have building X at height last, right? Okay, the problem is if last is really big. Okay, so if last is too big, then what can we do? How do we change our, like, is a annoying problem. Okay, how about I guess what I could try to do is find the height for each of the restricted buildings, their maximum possible bound. And so the way I would do that, I'd probably have to maintain some sort of stack, right? Sheesh, okay, let me see how many people solved this. Oh, 9 people, okay. Maximum pulse height of the tallest building. Okay, I think what I could try to do is maybe I could maybe create some sort of graph where so maybe I could create a graph, or not really a graph, but like I could sort restrictions by the maximum height, and basically when I take out something from restrictions, I set that to its maximum height there, then I update its neighboring two buildings, right? And I update those maximum heights, and then I put those into the priority sort of queue. So let me think about this. Height, maximum height, and so for everything restrictions, maximum height of restrictions of I of 0 is equal to restrictions of I of 1, right? And this is at the very beginning, and I'll set max height of 0, or 1 is equal to 0, because building 1 has height of 0. And now I have to create some sort of queue. I'll just use a set for this. Where I'll put basically all the elements of max height. So in.insert it.s, it.f, right? This is the height, and this is the index. So now while in is not empty, and I'll just store a set of indices too that we have restrictions on. Index. I'll put 0 in here. And index.insert restrictions I0. Okay, so I take something out of this, and I'll set our current index ID is equal to the first or second element, and int height is equal to the first element. Now I have to update its two neighbors, and so let's get the left neighbor. The left neighbor is the upper bound, it's the lower bound of ID minus 1, and if this is equal to index.begin, then there's no left neighbor. So if left not equal to this, then we subtract 1 from here, and L is equal to basically this. And I'll do the same with right, except we do upper bound. And if this is equal to right.end, not equal to right index.end, then we set our right neighbor as this. And now, so basically if the height of our current thing plus the distance, so I'll do abs of ID minus L, right? If this is less than or equal to max height of L, or if this is less than, strictly less than max height of L, then we have to update that. So this is sort of like BFS, and then we have to put that into the queue. So max height of L, max height of L, and then L. And we do the similar thing for the right thing. So if height plus abs of ID minus R is less than max height of R, then the right vertex will be set equal to H plus absolute value of the difference, and we can insert that in. Alright. Okay, so this will get the maximum height for all the things with restrictions on. And now, let's say we're given a left vertex with restriction X, so it has, this doesn't just get the restriction, this gets the height of all the IDs that we've given in the input. And now we have to fill in all the gaps. So we have a left vertex with ID, or with height X, and a right vertex ID, or with height Y. And so they have a distance of D between them, right? So I guess like from X, you have to go up some steps, then you're gonna go down to Y, or whatever. And you'll always be able to go up and then down or whatever, because what we did over here, because we updated our minimums. So I'll try to loop through that. So I'll create an answer, and so for all our things in max height, or I'll just keep a vector, to be honest. Int, let's put updated, and so for everything in max height, we'll just put this in our updated thing. Updated.pushback it.s, which is our vertex and our height respectively. And now so we basically have int x is equal to updated of I dot second. Oh, I should probably do this. Okay, so our int x is the left, and our int y is the right. And our int distance is equal to updated I of f. Okay, and now, so we're gonna go from x to x plus 1, to x plus k, then x plus k minus 1 to y. And so we want to find this k. So the number of elements here will be basically d plus 1, right? And so we'll have k plus, or we'll have k plus 1 here, and then over here we're going to have k minus 1 to y minus x. Let me see, to y, so x plus k minus y, I guess. So this is x plus k minus y numbers, and this is k plus 1 numbers. So the total number of numbers here is x plus k minus y plus k plus 1. And this has to be less than or equal to d plus 1, because that's the number of IDs. So I'll just do this. So we need x plus k minus y. So x plus 2 times k minus y plus 1 is less than or equal to d plus 1. I'll do this here, move the plus 1s. And so 2 times k is less than or equal to d plus y minus x. Okay, and so k is equal to the floor of d plus y minus x over 2. And so our answer is updated with x plus k. So I'll just set this here, int k, d plus y minus x over 2. Maximum of ants of x plus k. And we can return our answer. Okay, this is probably going to have a few bugs, so I'll have to debug. 205. Okay, so the 0 here. Oh, okay, this is when our updated size is what? If this only has one element, then if this only has one element, then from the last number here we can also update. So so int id is equal to updated dot back dot first, h is equal to updated dot back dot s, and this is equal to the maximum of our IDs start from 1, right? So n minus id plus h. 255. Okay, that works here. I think this is correct. Oh, let's go. Okay. Let me see what I got. What place? Okay, 83rd. Not bad. Okay, so let me explain my solutions. Number 4 took me a really long time compared to like the top people. Unfortunate. Oh wait, I'm gonna go up in rank. Never mind, because 25th is 35 minutes. Oh shoot, I'm gonna be top 30. Okay, cool. Let me refresh. Okay, this is gonna update in some time. Let me explain my solutions. I've never gotten top 30 on a Leetcode contest before, so that's nice. So, okay, number 1, given an integer n in base k, please return the sum of the digits of n after converting n into base k. So this is a pretty standard problem. Basically, we want to find n in base k, and we want to find the sum of digits, right? So, a very common algorithm to finding n in base k is the last digit of this will be n mod k, and then we can divide by k. And so if k equals 2, if we want to convert 10 to base 2, 10 mod 2 is 0, right? So we put a 0 here. We divide 10 by 2. Now we have 5. 5 mod 2 is 1. We divide by 2. We have 2. 2 mod 2 is 0. We divide by 2. Then we have 1 mod 2, which is 1. And then we divide by 2. And so we have 1, 0, 1, 0 here. And so the similar strategy is for general k, where you mod by k. That's your last digit. You add that to the answer since you want the sum. And then you divide. And you just repeatedly do this till you get 0. Okay, number 2. The frequency of an element is the number of times it occurs in an array. So you're given an integer array nums and an integer k. And so in one operation, you can choose an index and increment. I'm not sure if binary search is overkill here, but basically the first thing you want to do in this is you want to sort this in increasing order. So let's say you have A1, A2, this is your elements of the array, right? So basically it's optimal to make the most used index one of these elements, right? Because if you don't make it one of these elements, let's say you make it like equal to x, which is not one of the elements, then you're increasing some of these to x, but you can just increase it to the least element less than x, right? Or the greatest element less than x. And you're going to be using less operations, so you can potentially get a larger answer. And so let's fix the number that we increase all these numbers to. So let's say this number is equal to a of j for some j. Or I'll say I actually. So let's say it's equal to a of I. Now we're going to be incrementing a of I minus 1, a of I minus 2, all the way till a of j to a of I. And this has to be in less than or equal to k operations. And we increment a of I minus 1 to a of j because if we increment a of x to a of I, but we don't increment a of y to a of I, where y is greater than x and less than or equal to I, if we don't do this but we increment this, then that doesn't make sense because we could have incremented this in less operations because since our array is sorted, this is going to be greater than a of x. A of y is greater than a of x. And so it's going to take less operations to get of a of I. So that's why you want to take some sort of subsegment to increase. And so for each I, you can basically binary search this subsegment. You can calculate, because the number of moves it takes is a of I minus a of I minus 1, plus a of I minus a of I minus 2, and so on until a of I minus a of j. And so the number of operations here is a of I times I minus j, since this is all of a of I, and then we take the sum from I minus 1 to j of a of x. And so we have to make sure this is less than or equal to k, and that's basically our binary search. And so we just do this across all indices. We get the maximum for each index, and then we just set our answer as the maximum of all of them. Okay, number 3. Let me reload and see. Okay, cool, 30th. Nice. Okay, so a string is considered beautiful if it satisfies the following conditions. Each of the 5 English vowels must appear at least once in it. Alphabetical order. Okay, so basically what I did for this problem was 2 pointers. Let me just go somewhere else. Okay, so since you need this part sorted, let's say you have like this subsegment that works, right? So this subsegment works. That means this index over here. So you're going to have A to A, then E to E, then I, then O, then U, right? And that's the only condition where it really works. And then now this element is going to be something else. Let's say like it's an I or something. So we found this from the beginning. This is like one sort of thing. And now if we make L between, so our L is over here and our R is over here, right? So let's say we make our L equal over here. Then this R is going to stay the same if this new L is still inside this sort of box. Because we're still going to have A, E, I, O, U, then we're going to go to this bad index here. And so once we find this box, we can safely say that that box, this is the maximum answer for that sort of segment. Then we shift our L over here, and then we shift our R over here, and then we compute the new box and so on. And for this case, it's just going to return nothing, because this is an I. And then, but we might get an A, E, I, O, U later on, right? And so this is going to be our new box. And we just basically compute all these boxes and return the maximum size of one of them. And so the implementation, I didn't do it very well, but I just converted these to numbers to make it easy to work with. And then this is our last thing. This is sort of our condition for sorted. It has to be greater than or equal to the previous one, which is our last. And then we just find the box and see if the box works. This means we have all A, E, I, or U, and so on. Okay, number 4. Okay, this problem was kind of annoying. So basically, you're given a bunch of restrictions on these buildings. And so the first thing to note over here is that these restrictions, they can be very loose. And so you don't really know, you don't really know whether you can actually read these restrictions. So like, let's say the restriction for building, let's say we have building 1, right? And the restriction for building 7 was, it has to be less than or equal to 5. So I'll say 5. And now the restriction for building 9 has to be less than or equal to 1. So immediately off the bat, you can see that even if we go from 1 to 7 and we reach 5, since the adjacent elements differ by at most 1, we cannot hit 1 over here. That means our building 7, it has to be less than or equal to 3. Because if it's less than or equal to 3, then we can go 2 on 8, and then we can actually hit our restriction 1 on 9. And so this immediately gives rise to sort of like a BFS approach, where we basically sort our restriction by height, and we put all of our heights, all of these things into a priority queue. And so we take an element out, and when we take 9 out, we update 7 and its next right neighbor. And we can do this because since we're using a priority queue that's sorted, this is going to be less than or equal to the one on the left and less than or equal to the one on the right. And so those things can only really decrease, but they're never going to decrease less than this. And so once we update those, if it's possible to update, we'll put this in the queue, then we'll update one of its neighbors, and we'll put this, we can update one of its neighbors, and so on. And so at the termination of this, you're going to get a new sort of set of restrictions that you can actually work for each element. And so this is going to return 0, 3, 1 now. And now, so from over here, what you can do is now we want to compute the maximum, right? So what we're given over here, we were given a bunch of these indices and a bunch of these heights, but we have a bunch of these gaps that we don't really know what to do with. And so the most optimal thing for a gap intuitively is to go from 0, or from whatever number we have here. Let's say we have x, we go to some number x plus k, then we go down from x plus k minus 1 to y. And so the maximum k over here is what we want to compute, because that's our maximum sort of peak between these two buildings. And so that's basically what I did over here. I explained it a bit while I was coding, but if we're given the distance between two buildings and the heights of the left and right buildings, then we can calculate k by just seeing the number of elements in between. And so we just take the maximum of all of these and we can get the answer. Yeah, that's pretty much all. I feel like number 4 was a bit bashier than normal. Like, I think last week's number 4 was really easy. I solved it in like 2 minutes, but this one took a lot longer. But yeah, that's pretty much it. Thanks for watching. I don't know if I'll do these every week, but I'll see. Thank you and bye.